So, welcome everybody. We are very glad to have so much people. Thank you very much for attending. And well, today it's a great pleasure to introduce Viviana del Barco, who is in Paris now. And well, she will talk about purely coclosed G2 structures on nil manifolds.
Okay, thank you. Good evening and good afternoon to everyone. First of all, I would like to thank the invitation to speak. It's a pleasure for me to speak in this seminar, where is many people from Brazil and from Argentina, whom I've been very close to. Well, today I'm going to speak about the new subject I've been working with Andrei Morodianu and Alberto Rafero, who are also around here. I don't see anything but my screen PDF, so if you have any question or comment, you can interrupt. And I don't see the chat either, so you can interrupt. Okay. So, well, I will speak about purely coclosed G2 structures on nilmanifolds. We don't have yet the preprint, but we hope to be soon for next week on the archive or the week after. But we are almost done. So, coming soon. Okay, today I'm going to split the talk in three parts. First of all, I'm going to talk about some preliminaries on G2 and nilpotent and nilmanifolds and nilpotent groups, their geometry, and what is known in general about G2 structures. Then I'm going to talk about the work we've done with Andrei and Alberto, and we focus on the study of coclosed and purely coclosed two-step nilpotent groups, and therefore two-step nilpotent algebras of dimension 7. And at the end, I will make a brief summary of the results and well, comment on well, in general what we've done, the improvements. Okay, so first the preliminaries. To have a general, well, the definition, if you have a 7-dimensional manifold, it's just structure is defined through a differential 3 form such that verifies the non-degeneracy condition there. Every time that a manifold meets such structures, then you have automatically defined a metric and an orientation of the manifold, and therefore the Hodge dual. And it means that point-wise, your 3 form is going to be written in this way, and the dual of the 3 form is going to have the standard form of a G2 structure on a manifold. This is only point-wise. It means that for every point you find an orthonormal basis, but in general you cannot do it globally. Well, of course, well, in the groups it's a different situation. So not every 7-dimensional manifold meets such structures. There are obstructions. Topological obstructions. Okay, if we denote the Levi-Civita connection by nabla of the manifold, then there's a very well-known result saying that the 3 form is going to be parallel with respect to the Levi-Civita connection if and only if the allonomy of the metric is a subgroup of G2, and this is equivalent to the 3 form being both closed and coclosed. And this is why this is interesting, because of the special allonomy. And also it is known that any such manifold is Ricci flat. Well, when the 3 form is parallel, then the G2 structure is called parallel. Here I will talk about special three forms which are not necessarily parallel, but there are less restrictive conditions on the three form. For instance, we can consider three forms defined in a G2 structure which are closed or coclosed, only closed, only coclosed, let's say. And in this talk, I will also talk about purely coclosed G2 structures, which have been recently studied because of G2-structures systems, which are defined by a G2 structure which is purely closed up to a conformal change. So in general, what is the general theory? We know that for every compact seven-dimensional...
Sorry, Viviana?
Yes. Yes.
This purely coclosed, in terms of the torsion forms, I don't remember. It means that tau 0 or tau 1 is 0?
No, it's tau 3, I guess. I guess it's tau 3, 0. Well, it only has one element of the torsion. I'm not very familiar with it. Well,
shouldn't it have tau 3 non-zero?
It's tau 0 equal to 0. Sorry.
Tau 0, okay, thank you.
And also tau 2, right?
Yeah.
I think tau 3 would be the only non-zero component.
Yeah,
Maybe.
tau 3 is the only non-zero component.
Yeah.
Ah, okay.
Okay.
This comes from the sort of Strominger system. So the tau 0 would be the scalar curvature. You probably want that to be 0.
Yeah, tau 0
so
is
you only
0.
have tau 3. That's right. But it makes sense. It makes sense, right? Because if you want 0 scalar curvature, morally. For physical reasons, which is no reason at all, but you know.
Okay.
But that makes sense. It's a good thing.
Okay. Okay. So in general, it is known that every compact seven-dimensional manifold admitting a G2 structure that admits a coclosed one. So if you know that your manifold has a G2, then it has coclosed G2. The hard part here are the closed G2 structures, for which there are no general existence results. And actually, it was proved by Rafael and Podestá that compact homogeneous manifolds cannot carry any closed, non-parallel invariant G2 structure. So I'm not going to work with closed G2 structures, only co-closed. But in the invariant context, we also have some problems. So now I'm going to enter to the nilmanifold context. So this is the context we are going to work. And here my manifold is going to be a simply connected nilpotent Lie group, which is not abelian, of dimension 7. And the three form is going to be considered to be left invariant. That means that left translations of the Lie group, the multiplication, preserves the three form. So in this case, the metric induced is a left invariant metric. Also, the interest of working with simply connected nilpotent Lie groups is that when you have a lattice when the Lie group admits a lattice, then the three form can be induced to the compact quotient. Okay, so what do we know in this case? Always the Lie group and the compact quotients will admit left invariant G2 structure. So the topological obstruction here is solved because the manifolds are parallelly servable. Okay, and the question is of which particular type? Well, first of all, these manifolds are never Ricci flat. This is known already by the famous paper by Milner. So we don't have parallel G2 structures. So the general case is not going to work here. So we can restrict to the other less restrictive case. cases. Nilpotent groups admitting invariant closed G2 structures were studied by Conti and Fernandez in 2011. Actually, the first example, as far as I've heard, the first example of a compact manifold admitting a coclosed non-parallel G2 structure was made by Fernandez in one of these nilmanifolds. But okay, closed only manifolds are already classified. That means the Lie algebras admitting at least one closed G2 structure. What about coclosed in the same context? These were treated by Bagaglini, Fernandez, and Finn in 2011. They studied the Lie algebra isomorphism classes, let's say, admitting coclosed G2 structures, and they treated the general decomposable case and two-step nilpotent case completely. And they said exactly which are the Lie algebras admitting at least one coclosed G2 structures. And also they studied them in relation to Nilsson metrics. They were interested in whether these metrics, the Nilsson metrics, could be induced by these coclosed G2 structures. And actually they observed that even though the compact manifold always admit G2 structures, and therefore they admit coclosed G2 structure, there are nilmanifolds not admitting any invariant one. Okay, so this means that we can use the invariant context to construct the good examples, let's say, because even though the existence is guaranteed by a general theorem, the construction is not trivial, so we can do it. But at the same time, we may arrive to empty sets too. Okay. Okay, and now I don't see. It says also examples of purely coclosed. They are already in the literature, and they were also treated by Fernandez, Villacampa, and others. And there are examples, but we saw that there were, as far as we knew, there were any general study of these structures, at least on the manifolds. So in this context, for us, a G2 structure will be a three-form on the Lie algebra. Okay, since the three-form is going to be considered left-invariant, then we treat elements as we treat the invariant tensors on the Lie group as linear tensors on the Lie algebra. So for us, there are going to be three forms on the Lie algebra, and we denote lambda 3 plus the set of three forms satisfying this condition. And then we have this map. For every positive three form, we assign the metric that they induce. And this map is surjective, because every time we pick up a metric, an inner product on the Lie algebra, we can take an orthonormal basis and then define the three form, the standard three form, let's say. And this is a positive element, and you can check that this is induce the original metric, because we build it from an orthonormal metric, orthonormal basis, sorry. So this map is surjective. So here are our questions. First of all, I would like to notice that when we speak in this context about closed and co-closed structures, we are going, this is with respect to the Chevalier-Eilenberg differential of the Lie algebra, okay? So I'm going to put these notations, co-closed and purely co-closed, the sets of co-closed and purely co-closed. So first of all, our questions are, which Lie algebras have at least one of these structures, and which have co-closed and purely co-closed? So this was more or less the question that were already treated, for instance, by Bagaglini and also by Conti when working with co-closed. And this is the usual question, to say which isomorphism types of Lie algebras admit such structure. The advantage here, I have to say, I didn't say it before, that seven-dimensional nilpotent Lie algebras, real, are classified. So we can go through a list and say this one admits, this one does not. Okay. So this is the general approach for this kind of problems. Ours is a little bit different because we were interested also in the second question, which is the following. We know that this map is surjective. So we have in the algebra, we have this map that is surjective. So what can we say about the restrictions of this map with respect when we do have non-empty sets, let's say when we do have coclosed and purely coclosed. So this question rephrased would be, given an inner product on a Lie algebra, can it be induced by a coclosed? Can it be induced by a purely coclosed, if there is any? Okay. So our approach was starting from this second one, and we obtained also answers, of course, from the first one. Okay. So this was I think, one of our contributions in this aspect. So these are the questions. So with these questions in mind, I will start talking about the context, which is a little bit more restrictive, because these questions can be posed in any invariant context. Now we work in the two-step nilpotent Lie algebra, where this approach actually worked very well. So our context, we work on two-step nilpotent Lie algebras. This means that the derived algebra of, or the commutator of our Lie algebra is contained in the center. And so if we put an inner product on such Lie algebra, we can decompose N as a sum of vector spaces, which is N prime, and its orthogonal complement. So using the metric, we have the dual, which is, we identify the dual of N with the dual of R and N prime. And it is well known that the differential of the orthogonal of N prime, of the derived algebra, the differential of R in this case is always 0 of a dual element of R. And the differential actually is non-zero on N prime, and it arrives to lambda2 of R. This is usual for two-step nilpotent Lie algebras. And in this case, since we are taking the differential from N prime to lambda2 of R, this is injective. And therefore, we can see that if N was 7-dimensional, which I didn't write it, but if N is 7-dimensional, then the dimension of N prime is less than or equal to 3. This is important because we treated the cases dimension of N prime equal to 1, to 2, and to 3.
Can I ask a question?
Yes.
Why do you need an inner product? Why do you need, I mean, you still have a direct sum. You can still speak of dual elements in the dual.
Yeah, no, in general, you don't need. No, you don't need. You don't need to take the differential. You don't need it.
Right. Okay. That was my impression. You don't need orthogonality here, and even if you did, then you would probably need some sort of compatibility between the differential and the metric. So you probably don't even want to do that.
No, actually, what happens in the two-step nilpotent case is that you can define, as long as you take an injective map from N prime to lambda2 of R, you always have a two-step nilpotent Lie algebra because you don't have a Jacobi identity to verify.
Mm-hmm.
The Jacobi identity on two-step nilpotent Lie algebras is trivial. So the only thing you need is to have a differential. I mean, if you don't have an inner product, you'd need a differential from the dual to lambda2 of the dual of another space, and then you can construct a Lie algebra.
Right, and that's fine. right? So orthogonal
Yes.
is just to simplify the picture.
Yeah, actually, because we are going to work with metric Lie algebras.
Sure.
That's why.
Right.
That's why.
Right.
But no, in general, you don't need it. No.
Okay. Right.
And okay, so this I wanted to point out that this construction can be reversed. Actually, if you start with two inner product spaces and you have an injective map, then you can build a two-step nilpotent Lie algebra by defining D, as I said before, as the defining for the Lie algebra structure. And as I said before, this works because you don't have Jacobi identity to verify in this case. I'm not going to use this precisely in the talk, but this backwards construction is useful in this context because I'm going to give conditions for a purely coclosed or a coclosed G2 structure to be closed, a coclosed, sorry, depending on the differential here. So if at any time we want to build a G2 structure, and the only thing we need to do is to pick a D, a differential, so that the conditions I am giving are satisfied. Okay, that's but I'm not going to use it explicitly, but this is useful to build explicit examples. Okay, so which are our techniques? We start with a two-step nilpotent Lie algebra of dimension 7, and we decompose it as I said. And we're going to work in each case separately. Okay, and in each case we're going to work with G2 structures which behave well with respect to the Lie algebra structure. What does it mean? And here I'm going to lie a little bit, but it's more or less like this. We are going to pick, in general, a G2 structure which has this form. Phi is going to be sigma 1, wedge E5, wedge E6, wedge E7, and 5, 6, 7. Where E1 until E4 will be elements in the R part, so their differential is 0. And sigma I will be self-dual forms in R, or sorry, it would be self-dual forms in the four first elements. So the differential is going to be 0. So this is the first part. In addition, a basis of n prime is going to be contained in 5, 6, and 7. So that the structure of the Lie algebra, which is only determined by the D, is going to be determined by D of E5, E6, and E7. Okay? So notice that n prime can have dimension 1, 2, or 3. Okay, so for dimension 3, this is going to be the case. For dimension less, then we are going to have only 2 elements here between 5, 6, and 7, which are in n prime. So the idea is that for these forms, it's easy to compute the differential and also, well, the Hodge of the dual of phi, and also the differential of the dual of phi. So the idea was always in the 3 cases, try to adapt our G2 structure so that it is adapted to the Lie algebra structure and make the things nicer. So in each of the cases, I'm going to give necessary and sufficient conditions for phi to be phi of this nice form, let's say, to be coclosed, and also necessary and sufficient more restricted conditions for phi to be purely coclosed.
So these conditions of well behavior can be assumed up to equivalence? Or?
Yes, well, this is, I'm going to talk about that. Actually, when you have a G2 structure, you have a liberty. You have a G2 structure, then you can take an adapted basis, let's say, and then you have the liberty, since G2 acts transitively on pairs. Only if you pick two unit vectors, you can choose, I don't know, maybe the last 2 to be these two unit vectors. Let's say that n prime has dimension 2, then you can pick them, like, I don't know, 6 and 7 to be an n prime. But then you don't have much liberty to choose the other ones. And that was one of the problems. But we managed to solve it in some way. But we always start, the idea is we start with something of this form, we find the conditions, and then we prove that we can always achieve them.
Okay.
But yeah, it's not actually, it was the non-obvious part, but this is to more or less say the general picture.
Great.
Okay, so now we start in the 4. We have to make the 3 cases, and I don't think I'm going to do them all. So, okay, as I said, dimension of n prime equal to 1. This, okay, I said these Lie algebras are classified for 2-step nilpotent. This is a finite family, a finite number of Lie algebras. And to have in mind, these are the Lie algebras having n prime of dimension 1. R4 plus H3, R2 plus H5, and H7. These are the Heisenberg Lie algebras. Okay, so we start with the metric Lie algebra, and we decompose it, as I said before, R and n prime. And here I'm going to use a little bit of SU3 structures, which, well, I'm not going to introduce. So I am going to assume them. But if you have a unit vector and you have a G2 structure, then you can, here we take the unit vector on n prime, spanning the one-dimensional n prime that we have, and we can always write them as in formula 3, where phi is omega wedge the z flat plus psi plus. The Hodge dual can be computed in the other part, and where the psi plus, the omega psi minus, they all correspond to the SU3 structure, and they behave as in formula 4, more or less. Well, this is more or less well known. And notice that I've introduced J because I'm going to use it to say the conditions for phi to be coclosed. So I'm going to denote A, the skew-symmetric map on R, which is defined by the differential of Z. Remember that since Z is on n prime, the differential is in lambda 2 of R. Okay, so it's going to define an element in SO R. So phi is going to be, the proposition says that phi is going to be coclosed if and only if J and I commute, and moreover, it's going to be purely coclosed if and only if the additional condition of the trace of J times A equals to 0 holds. Okay, so notice that that's why I was saying before that I lied a little bit, because here we don't have the structure. I didn't write phi as sigma wedge something, but these are hidden in the formula 3, where phi is written now as omega wedge z plus psi plus. Okay, in the next one is going to be identical, but in this case, since we reduce everything to SU3 structure, actually we use the identities for the proof. You can see that you can take the differential of star phi, and you're going in formula 3. The differential here, since omega is closed and psi minus is closed because they live on the R part, then the differential of star phi is only psi minus wedge d of z, and d of phi wedge phi is omega squared wedge d of z wedge z flat. Okay, so and these conditions, if you want to write them in terms of J, actually they say, the first one says that A and J commute, and the second one says that the trace of J times A is 0. So this is what I was saying. Now for phi, we have some conditions for a well-behaved phi. We have a condition to be checked to be closed and coclosed. So this is our first theorem. If we take a metric Lie algebra with dimension of n prime equal to 1, then there's always a coclosed G2 structure inducing the metric. And there exists a purely coclosed G2 structure inducing the metric if and only if the trace square of A squared equals 4 times trace of A4, A to the 4. And we rely on our lemma, on our previous lemma. So how is this proof? We start with the metric Lie algebra, and we pick up a unit length vector spanning n prime in this vector. So we start with the metric, and we want to build a phi, and we are going to build it using the previous lemma. So I start with a Lie algebra and a unit vector in n prime. I take A as the skew-symmetric endomorphism defined by D of Z. And so there exists, since A is a skew-symmetric map in a 6-dimensional space, then there's always an orthonormal basis such that A has this form with ABC reals, okay? So what we're going to do is to pick up this SU3 structure induced by these spaces. So that means that omega is going to be the standard one and psi plus is going to be the standard one. And so J is going to be the standard one. So that means that J, instead of A and B and C, I put only ones. So that's the J. And actually, it is easily seen that J and I commute. And then I just build phi of the form I had before. So this is co-closed because J and I commute, and since the basis I've taken is orthonormal for the original metric, then the metric induced by the co-closed form is actually the original metric. And for the purely co-closed condition, we can check that the trace of I A times J is actually A plus B plus C, if A has this form. So phi is going to be purely co-closed, the one I defined, if and only if A plus B plus C equals to 0, and there is a nice condition, which is expressed in terms of the trace. You can verify that this is the same. So what we get here is that, as I said before, we give a condition for a co-closed. In the lemma, we gave a condition for phi to be co-closed. And in the first point, we proved that this can always be achieved. And the second one is a more restricted condition. And actually, it says A plus B plus C equal to 0. So from here, we can get actually that H3 times R4 does not have any purely co-closed G2 structure, because this Lie algebra corresponds to only one of A, B, and C being non-zero. So if B equal to C equal to 0, then I'm never going to get the trace condition to be satisfied. So if you want to study the pairs of nilpotent Lie algebra, two-step, with a metric, which are such that the metric is induced by purely co-closed, then the first thing I'm going to say is that R4 times H3 does not admit any purely co-closed G2 structure. It admits co-closed, but any purely co-closed. Also, you can see for R2 times H5 that any metric can be expressed as in this form. The metric, if you have the Lie algebra which is isomorphic to this one, then the metric can be written using the parameters R and S, and this metric, any metric can be written in this way, and any such metric is going to be induced by a purely co-closed if and only if R equals to S. Notice R and S are in F1 and F3, and for H7, this you have 3 parameters, and we ordered them so that they are non-isometric with different parameters. And the metric is going to be induced by some purely co-closed if and only if the last condition is verified. So, okay, before going to the second dimension, so in this case, we get that any metric can be induced by a coclosed, but for in any case, we get metrics which are induced by purely coclosed and metrics which are not induced by any purely coclosed. Okay, so what happens for dimension of n prime equal to 2? I have to say that, well, each case has the n prime equal to 1 was the easiest, but now the two following have a particularity. Each one of them, they are not the same. They are similar, but not the same. So again, these Lie algebras are classified. And we have this 1, 2, 3, 4, 5, 6 Lie algebras. And I'm going to say that the first 4 are decomposable and the last ones are not decomposable. That means that they don't have an R factor. Okay, so the first thing we're going to prove is, well, we start with a two-step nilpotent Lie algebra with dimension of n prime equal to 2. And the first result is to show that if we have a coclosed G2 structure, then for any basis of n prime, the vector z1 interior z2 interior phi lies in the center intersection n prime orthogonal. This means that, in particular, your Lie algebra is decomposable. So I'm going to go back. So in this list that we have in dimension 2, this proposition says that the last 2 Lie algebras don't have any coclosed G2 structure. Even though we start with the Lie algebra with a metric, we obtain the result for Lie algebra isomorphism classes, let's say. Okay, so this was already known. I have to say this was already known because when Bagaglini, Fernandez, and Fino they studied coclosed G2 structures, since they were classifying the isomorphism classes, they already knew that these 2 Lie algebras didn't have any coclosed. But the difference is that their study was done using the classification, and actually we go in a different way, and then we use the classification to express the results, let's say. Okay, so we start with a coclosed. How do we prove this? And actually, in the proof of this, we're going to get the conditions for a G2 structure to be coclosed or purely coclosed. So we start with the coclosed G2 structure, and we take an orthonormal basis of n prime, which is of dimension 2. And we can use, as I said before, we can use a G2 element, an element in G2, to say that there is an orthonormal basis of the Lie algebra such that the 2 last elements, sorry, in this case we use 5 and 6. 5 and 6 are Z1 and Z2, and phi has this form. Okay, so we started with a coclosed G2 structure, we take an adapted basis, which always exists, and then we use the transitivity of G2 on unit pairs of unit vectors, so that we can put our 2 elements in n prime as 5 and 6, and the 5th and the 6th. Okay, this is what I was saying before, Jorge. When you ask, you can always do it. It's not guaranteed, but at some you have some liberty. Of course, I didn't know. I learned all this. So in particular, E7 is with phi of this form. E7 is the vector that is expressed in the statement. Okay, Z1 interior Z2 interior phi is actually in this base is E7, and we want to E7, and then the vector corresponding to E7 is going to be the one which is in the center and not in n prime, of course, because E7 is orthogonal to n prime. So we want to prove that E7 is in the center. Moreover, as I said before, the differential of the E case is 0 for any k 1, 2, 3, 4, and 7, because 5 and 6 are the only ones which are in n prime. So those are the only ones which have non-zero differential. For all the others, it's 0. And we have R, which is 1 until 4 and 7, which is the orthogonal of n prime. And we call R tilde actually the complement of 5, 6, and 7. So we decompose the differential of EK for 5 and 6 as something in R tilde, something in having components from 1 to 4, plus theta wedge E7. And the fact that E7 is in the center is equivalent to showing that theta 5 and theta 6 are 0. So, and this is the, I think, okay, the most extensive result I'm going to talk. So we have this, we want to show that theta 5 and theta 6 are 0 because phi is coclosed. So what we're going to do is to put an orientation on, we put the orientation on R tilde, and we take a basis of self-dual forms. So we can write phi in the way I said before, sigma 1 wedge E5, sigma 2 wedge E6, sigma 3 wedge E7 plus 5, 6, 7. So again, we use the formulas for the differential and the metric to compute the differential of star phi, and we get this condition. So if we want phi, if we know that phi is coclosed, then each term is 0. Because if you can see that the sigmas and the betas are only have components from 1 to 4. Okay, so you have the wedges with 6, 7, and 5, 6, 7, and 5, 6, 7. And the thetas also are from 1 to 4. So phi is coclosed if and only if each of these terms are 0. Okay, so in particular, the last equation, together with the fact that sigma 3 is a non-degenerate 2 form on the R4 side, implies that theta 5 and theta 6 are 0. So we get that d of E5 and d of E6 are in lambda 2 of tilde R. So this implies, you can follow the computations, this implies that E7 is in the center, and actually it's orthogonal to n prime. So this means that n decomposes as a sum of orthogonal ideals, and in particular, this is decomposable. Okay? So as I said before, the 2D algebras which are not decomposable, in this case, do not have coclosed G2-structures. Okay, this is the proof of the theorem, but actually we've done a lot of work here. Actually, we didn't use, for instance, equation 6. And so I've written again the same system, and I added the condition for phi to be purely coclosed. And there we get a different condition. Well, one more. And recall that when you have self-dual forms, when you have two forms, if you make the wedge product, you are making actually the inner product as dual forms. So the system which is above, or the system I will get by imposing phi to be purely coclosed, that means the last equation to be 0, is equivalent to talk about the components of the self-dual parts of beta, which are the differentials of E5 and differentials of E6, in the self-dual part of in sigma 1, sigma 2, well, and sigma 3, which means it says it's 0. Okay, so the equation, we can write it as phi is going to be coclosed if and only if theta 5 and theta 6 are 0. And we have this equation, this system. Notice that this the matrix A, B, and C is symmetric. And this is going to be purely coclosed if the trace of this matrix is 0. So, well, this I've written again. M, if I denote M as the matrix with the components, then the conditions above translate. Phi is going to be coclosed if and only if M is symmetric, and purely if the trace is 0. And also, you can read them as conditions for orthogonality of the betas and also the length condition. Because notice that if, for instance, if it is purely coclosed, then I get A, B, B minus A. So beta 5 and beta 6 are orthogonal. Okay? So very quickly, this is the theorem of, in this case, it says the following. It says that, so reinterpreting, let's say, these conditions. Sorry, I'm going to go back. So we started here, we started with a G2 structure and we adapted the basis for the n prime, okay? So the theorem now says we can go backwards. And it says that if you have a two-step nilpotent algebra with dimension of n prime equal to 2, then it always has a coclosed G2 structure, provided it is decomposable. So n is going to admit a coclosed G2 structure inducing the metric if and only if the center intersection of n prime is orthogonal. Sorry, there is something in the center intersection of the orthogonal of n prime. And here I'm using the fact that if you have a 7-dimensional decomposable the algebra, then you have an error factor in the middle. But well, the second part is the most important, I guess. Well, both are important. That the metric is going to be induced by a purely coclosed if and only if there is a 4-dimensional subspace R tilde, such that the differentials of n prime are contained in lambda 2 of R tilde. This is going to say that the algebra is decomposable. And for every orthonormal basis of this should be n prime star, the dual, the self-dual components are orthogonal and have equal norm. Okay, so this condition is expressed in the previous condition on the matrix on the system I said before. So we just proved from the previous reasoning that if I have a coclosed G2 structure or a purely coclosed, then the only if parts are proven. Okay, I know this is decomposable, and I know that the self-dual parts are going to have equal norms and be orthogonal. Okay, so the only thing I need to prove is that if it is decomposable, then I have a G2 structure inducing the metric, and if I have the condition on the self-dual parts, then I have a purely coclosed. And I think, let me check. Okay, just say this.
So, Viviana?
Yes.
Yeah, in the case of dimension of n prime 1, the condition, both the condition for the existence of a purely coclosed was in terms of the Ricci eigenvalues. I mean, you can write that in terms of the set of Ricci eigenvalues very easily. I wonder, what about this number 2? Do you know if you can write in terms of the Ricci eigenvalues, the condition, maybe in a more neat way?
I don't know, but that's a good question.
Okay, thanks.
No, that's interesting, but no, we didn't check that. Yeah, this G said, yeah, are linked to this J set, but this is like the self-dual part of the J set, which give you the Ricci tensor. So I'm not sure, but that's a good point. Okay, just comment on this proof. So I said I have to take the condition and prove that there is a coclosed or purely coclosed induced in the metric. So for the first point, I start with an element in the center intersection of n prime, which I suppose is non-empty, and I take 5 and 6 elements on n prime, which are also orthonormal and of unit length. And then I consider an orientation on the orthogonal of 5, 6, and 7, which is 4-dimensional. And in particular, beta k, which are the differential of ek, lie in lambda 2 of r star. This is because E7 is in the center. I'm sorry, it should be E7 below and not above. So what we do here is we consider the plane in the self-dual, in the space of self-dual forms of R tilde, which contains beta 5 and beta 6. They could be 0. Beta 5 dual and beta 6, the self-dual components, they could be 0. So we cannot take the plane spanned by them, but we take a plane containing them. And we can always assure that there is an orthonormal basis of this plane, sigma 1 and sigma 2, such that the matrix is symmetric. And here we use the polar decomposition. We take any matrix, we write them, and then we use the polar decomposition to change possibly the basis, the original basis, and then we make them symmetric. And then we act. The problem is that these sigma i's could be not the standard ones that we need, because the sigmas, remember, were defined in a standard way, and we made all the computations using this form. So what we do is we know that we have a sigma 1 and sigma 2, so that the matrix is symmetric, and then we act by SO4 on pairs of, again, orthonormal sets of the same length, of the same norm. And then we modify the basis of, we can find a basis of R so that the sigma 1 and sigma 2 are of the standard form, and we keep the matrix to be symmetric. And in this case, so in this way, we build a basis. We started with 5, 6, and 7, and we picked with this procedure 1 until 4. So we arrived with an orthonormal basis of n. So we can take the G2 structure defined by this basis. So we know that this defined the metric, and because of the computations we did before, we know that since the matrix M is symmetric, then it's going to be coclosed. And I didn't write the part for purely coclosed. But the thing is that if we make this procedure and we arrive, for instance, if we start with a basis such that for the second case, if I start with a basis, I mean, with an oriented 4-dimensional subspace such that for every orthonormal basis of n prime, the self-dual parts are orthogonal and have the same form, the same norm, then when I modify this, I still keep the matrix M to be symmetric and trace-free. So in this case, I will arrive the G2 structure for the spanned by the basis. It's going to be purely coclosed. So this is more or less the procedure we did. So I will not have much time, but just finish with this case, which, so we have here any metric is going to be induced by a coclosed G2 structure, and is going to be induced by a purely coclosed if this condition is satisfied. So the question is, which conditions satisfy this, the second condition of which metric the algebra satisfy the second condition? So the idea here is that we know that if the Lie algebra admits a coclosed G2 structure, then it is decomposable and has a one-dimensional factor. So we go to dimension 6. If we go to dimension 6, we arrive to this n0, and now the condition in the theorem says that the n0, the 6-dimensional Lie algebra, has to admit an orientation on R0, which is the orthogonal to n prime inside AmSur, such that there is a basis of the dual of n0, such that the self-dual parts are orthogonal and have the same norm. So we arrive to 6-dimensional, and n0 is going to be one of these 4 Lie algebras. And we had the advantage that the metrics on these 4 Lie algebras, they were classified up to also automorphism. So for each Lie algebra, we know that there is a standard form for a metric. So we are going to do as in the first case. So these metrics were classified by Biscaglia and Reggiani and Vittoni. Vittoni, we found out Reggiani gave a seminar, so we found out. And so taking their classification, this is only the first case, this is the classification. So we take a 6-dimensional Lie algebra, and we know that if, for instance, n0 is the complex Heisenberg, then there is a basis such that the differentials are of this form, and the metric is isometric to one of the formulas here with F1, and here we have a parameter R, S, etc., etc. And well, for the other cases too. So what we did, and I'm not going to make more proofs. So what we did was actually saying, okay, for instance, this is one of the kind of propositions we can prove. If we have a Lie algebra, 7-dimensional Lie algebra with this metric, such that the restriction is given by the standard one of the parameters E, F. For instance, in this case, we have E, F, and R, and G. Then it's going to be induced by a purely coclosed if and only if F equals to 0, and G can be either E times this factor or the other factor. And these two options correspond to the 2 different orientations we can put on the 4-dimensional plane. Okay, so I'm not
check if the nil soliton is there.
Yeah, that's a good question. Good question. I don't think I checked. Well, I don't remember this particular case, but we know we've checked that nil soliton metrics and purely coclosed and metrics induced by purely coclosed are not related. We have examples. For instance, in H5 times R2, the nil soliton matrix is induced by a purely coclosed, but for H7, no. And also for H3 plus H3, the nil soliton metric plus R, the nil soliton metric is not induced by purely coclosed. Well, I don't have the exact list here, but we've checked them. We've checked them. I can say to you.
Great, thanks.
Welcome. So we made this classification in each case. So I'm going to only present the results. So for instance, for this Lie algebra, we get that G is going to be induced by a purely coclosed for these values of the parameters. For the other, okay, G equal to E. And the last one is here. This is H3 plus H3 plus R. And as I said before, the product metric is not induced by any purely coclosed. And actually, the nil soliton metric, or up to a scale, is the one given the product metric. So we see here clearly that they are not induced by purely coclosed. So I'm just going to skip the dimension of n prime equal to 3, just to say something about the possibility of choosing phi with respect to behaving well, as I said before, with respect to n prime. Here, remember what we had before was the transitive action of G2 in a pair of orthonormal vectors, which was good for n prime of dimension 2. But for n prime of dimension 3, we have 3 unit vectors. So we were tempted to use calibrated 3 forms. So that means in the form which is written here, phi, which means that 5, 6, 7 is spanned by n prime. So we started with working with this, but actually we were able to prove that this is not guaranteed by transitivity of G2 action. This was only, we started working with this, but I'm going to skip everything. But what actually we can prove is that if we have a purely coclosed G2 structure inducing the metric, then we have one which calibrates n prime. So we can put 5, 6, and 7 on n prime. Okay, and this makes why we want this, because of course it's much easier to work with this. This is in general. If we have a non-calibrated a G2 structure not calibrating n prime, you can have one inducing the same metric and calibrating n prime. But actually, we can prove that in no, I didn't. Did I write it? No. In any case except one, n prime is always calibrated. This is the similar condition. This is a similar theorem as before. Any G2 structure, any metric can be induced by a G2 structure, and we get some condition on the self-dual parts and with a matrix, with a trace condition. And here we don't have a classification of metrics, but we can go, as I said before, case by case, and say that any purely coclosed, any Lie algebra, admits purely coclosed G2 structures, and also possess metrics which are not compatible or not induced by any purely coclosed G2 structure in each one of the Lie algebras. Just that. So the results, as I said before, talking in this graph where we have the function g, which is surjective. So we can say that the Lie algebra admits coclosed G2 structure if and only if it is not isomorphic to the 2 cases where we're not decomposable for n prime equal to 2. Also, there are the only Lie algebra not admitting purely coclosed, but admitting coclosed. I'm sorry, I forgot the C. So PCC is empty and CC is non-empty. Is the R4 times H3. This is the only case.
Do you know which one is quaternionic Heisenberg, the H type?
Yes, it's dimension. It's not written as well. Wait. It's n. I don't remember the name.
But I mean, is special?
Yeah. No, it's yeah, it's one of these. Yes, quaternionic Heisenberg. You mean with dimension of n prime equal to 3?
Yes, 4, 3. Yeah.
Okay, it's 7, 3D. So no, it's
so it admits.
It admits, and actually all the coclosed are calibrate n prime. Yes,
okay.
It admits.
Thanks.
With respect to the surjectivity of the map, we can say that whenever you have coclosed G2 structure, then the map restricted to the coclosed set is surjective. So any metric in any case that we studied, if you have coclosed G2 structure, then any metric is induced by a coclosed one. And this does not hold for 3-step nilpotent Lie algebra. This was already known by Bagaglini, Fernandez, and Fino. They give a 3-step nilpotent Lie algebra, actually not inducing any soliton metric. Yes, this was the example. And we saw also that even if we have a purely coclosed G2 structure, the map is never surjective. So we have metrics which are not induced by any purely coclosed, and we have metrics which are induced by purely coclosed, of course, if it's not empty. And okay, and this was all, I guess. So thank you very much. Sorry for the late.
Okay, are there other questions?
I have one question.
Okay.
Can I just make an announcement just before people leave, just real quick?
Yes?
Yes.
Okay, so just so please everyone, you'll find in your chat the instructions to subscribe to our mailing list, and also to receive a reminder about WhatsApp if you prefer. So you can add us here, and this talk has been recorded, and it will be available on our YouTube channel, which you can find here. Okay, and then I have another announcement, but let me do that after the question.
Okay.
Okay.
Let's go with the question.
I have a question.
Okay.
Apart from the comment on the last slide, do you have any other reason for considering two-step nilpotent algebras?
Well, as I said before, the Lie algebraic structure is the simplest. So this actually was used all the time and very strongly. The fact that you have a part where the differential is 0 and a part whose differentials lie in lambda2 of the first one. So you can see them as skew-symmetric maps. If you already go to 3-step, or if you grow in step of nilpotency, then the formulas are become much involved.
Okay, thank you.
Welcome.
Okay, any other question or remark? Okay, let's thank Viviana again.
Thank you.
Okay.
Thank you for attending.
Right.
Thank you, Viviana.
So